I don't speak Portuguese, but I will. Gostaria de agradecer aos organizadores do Congresso por me convidarem para participar. Estou muito feliz e me sinto honrado de estar aqui. Before I start the presentation, I had a couple of slides. A couple of weeks ago on the internet, I found a photograph that looked like Canada, and the text that came with it was saying that the people here were pretty upset, and there was quite a commotion because of snow. Well, I wanted just to let you know that it can be worse. Where should I point? Anywhere? Yeah, it could be worse. This is a winter in Quebec City. 3.5 meters of snow every winter. In 2008, when this photograph was taken, we had 5.5 meters. I'll tell you, even for a Canadian, that's too much. Okay, I was asked at this Congress to talk about the impact of conservation agricultural practices on the emissions of N2O and ammonia from agricultural soils. Let's start with a common understanding of what conservation agriculture is. Well, it can be defined as a way to farm the land in order to produce enough food, and also make a good living, but with a special aspect that you want to preserve the resource and protect the environment. I think it is fair to say that most of the practices that have been proposed and adopted in conservation practices aim at dealing with water and sewage use. And at the beginning at least, there was not much preoccupation about what would be the impact of those practices on atmospheric quality. So it's exactly the question I will try to answer today about the impact of those conservation practices on those two gases. And we'll also try to go a little bit further and trying also to see how we can minimize these emissions by selecting the best practices. I don't speak Portuguese, but you will find Portuguese on my slides. Thanks to Professor Ciência of Santa Maria University, and also Ezequiel that introduced me, that graciously volunteered to put some Portuguese on my slides. If ever there's a mistake, I apologize, because I did translate some of the text on Google, so it's not that it won't be Cecil's fault, it's going to be mine. Okay, so I'm going to talk about those two gases, N2O and ammonia. For N2O, we spent a few slides talking about how it is produced, what is controlling the production and emission, in order to better understand how the practices actually can influence the production and emission. Those practices I will talk about today for N2O are plantio diretto, no-till, and fertilization, adapted to the no-till situation, introduction of legumes in the crop rotation, as well as the use of cover crops. As for the ammonia, there's essentially, no-till is the perfect storm for ammonia, perfect situation for huge losses of ammonia. So we'll only deal with how to manage the ammonium-rich materials like urea and animal slurries in no-till. Can we inject them? What will the irrigation and rain do about those emissions? Crop residues, are they friends or enemies, in this combat to limit the ammonia emissions? And finally, we'll see if urease inhibitors can be of any help. Okay? So why do we care about N2O N2O? Well, we care about N2O because now that we have pretty much decreased very much the emission of CFCs in the atmosphere, N2O is not the main gas, the main molecule actually responsible for the destruction of stratospheric ozone that is protecting us against too much UV radiation from the sun. And the other reason, of course, and that's why I'm here, it's a very powerful greenhouse gas. On a mass basis, it's about 300 times more powerful in terms of trapping the infrared radiation than CO2. Concentration has been increasing steadily since the Industrial Revolution. Where is produced N2O? Well, agriculture is responsible globally for close to 2/3 of the total anthropogenic emissions. And of these emissions in agriculture, soils are responsible for half of them. So when you think about the global N2O emissions, agricultural soils are responsible for about 30% of them. So how is it produced? Well, it is produced by the mostly microbial, but sometimes also chemical transformation of mineral nitrogen in soils. Originally, about 25 years ago or 30 years ago, we thought there was pretty much only nitrification and denitrification that could produce N2O. Now we know that there's more than 10, I don't know how many, that have been identified as potential sources of N2O. But we still agree that most of the N2O that is emitted from agricultural soils actually come from nitrification and denitrification. In the nitrification process, I'm not sure if the microbiologists agree on how really the N2O is produced, but there seems to be linked to a process to get rid of nitrite, which is very toxic when it accumulates during the reaction for some reasons. So this is usually what we believe is producing N2O during nitrification. In the nitrification, it's much clearer because N2O is a free intermediate of the reaction. So any nitric N that is denitrified will obligatory, compulsory, has to pass in the form of N2O before it reaches the N2, the molecular nitrogen form. So if this occurs pretty close to the soil surface, it may actually escape and contribute to the emissions. Why are agricultural soils a source of N2O? That's a legitimate question, because most of the natural soils don't emit N2O. Most of them. Most of the natural, in natural ecosystems, you won't see significant N2O emissions. Actually, some of them could actually be sink of N2O. So why are agricultural soils that leaky, you know? Because we also lose nitrate, and there are other forms of them losses. Well, we do bring massive, important quantities of nitrogen at once, very, very often, to compensate for the N that is exported with the harvested products. Doing so, we create a situation for a period of time after the application when the soil mineral N is very high and it is prone to losses. Practices also have pretty much always developed for increasing yields and decreasing costs, and environment is a fairly recent concern. So agricultural practices are keys, very key, a key role in controlling the factors that control N2O production. And we'll see more specifically what do the conservation practices do. Well, the most famous or known or widely used conservation practice is no-till. Snyder et al. In 2009, in an excellent review on the impact of agriculture practices, agronomy, and fertilization on N2O production, concluded that there's not a clear response for the mitigation of greenhouse gas emission using no-till practices compared to conventional. Let's see why. What brought them to this conclusion? Well, there are three gases that can be emitted or taken by soils. There's methane, CO2, and N2O. Methane, the amounts are so small that it doesn't matter if we multiply them by 3 or we decrease them to 0. It won't make a big difference in the greenhouse gas balance. CO2, when you adopt no-till, because mostly of the increase in carbon stocks in the soil, especially in the first years, you've got the sink of CO2. So that is clear so far. So what is that clear? It's really the N2O. What is the response of N2O emissions to the adoption of no-till? We'll see that it can be both ways, increase or decreases, and we'll try to see what could be used to predict if we would get higher or lower emissions. This is a work by PHILIPPE in the theme of Dr. Bayer here in Brazil, who did a greenhouse gas balance of the system here in Brazil. So you have the three gases. You'll also have the emissions related or associated with the cost fuel, essentially, of the agronomic practices, and finally the balance there. So we look at methane, and you see that methane is never a big issue. In the situation that these scientists were studying, it was early after adoption of no-till, and there was a major increase in carbon stock. So in this case, a very negative flux. So a negative flux is a flux from the atmosphere towards the soil of CO2. N2O, in that case, was also greater on conventional than on no-till. So adoption of no-till in that situation also decreased the emission of no-till. So not only increased the CO2 sink, but decreased the N2O source. Pretty much equal values for agronomic practices, so the balance is a major sink of greenhouse gases in that system. But the situation could have been a little bit different. Just imagine a situation where you could still have this massive increase in carbon stocks, but instead of having lower emissions in the no-till for N2O than conventional, you get the reverse, so the higher emissions in the no-till. And the same thing for the other one. Well, what you see there is that the change in N2O emissions due to no-till can have a major effect on the greenhouse gas balance. In this case, we went from a very, very important sequestration to a much smaller one. And in some situations, it may just very well offset the benefit of the CO2. So what is the situation in a no-till field compared to a conventional? Well, in both fields, the plant residues are returned to the soil. The big difference, of course, is that in conventional, the residues are mixed through the plow layer while they accumulate at the surface of the no-till. Theoretically, what does it do for the N2O? We were thinking about N transformation, nitrification into nitrification, and the N2O that can be emitted. Well, there you have the no-till. In the accumulation of organic matter at the surface, which ties up nitrogen in the soil organic matter. It's going to decrease carbon availability. It's going to lower temperature because of the mulch at the surface. It will keep substrates closer to the surface where oxygen from the atmosphere is just nearby. So likely better aerated situation. So all these tend to decrease the potential for N2O emissions. On the other end, you'll have more concentrated substrates, all at the soil surface rather than mixed through the plow layer. There will be an increase of water content because of the lower evaporation because of the mulch. And you have very often a higher rock density, so lower porosity, so lower aeration. All these tend to increase emissions. So the question is, when all those forces act together in the same field, what is the net effect on soil N2O emissions? Here I summarized what I found of direct comparison between conventional and no-till in Brazil. I found 6 studies. I'm sure there are more. I apologize for those that I didn't find that are not included. But of those 6, 5 out of 6 measured lower N2O emissions in no-till compared to conventional tillage, for an average of 43% less. So what we see here is that the data from Brazil seems to indicate so far, because I'm not sure if all the situation in Brazil, and you've got the large countries with contrasting soil types and contrasting climates and practices, but so far the data seems to indicate that under your conditions, no-till would reduce N2O emissions compared to conventional. But it's not the same everywhere. These are data from Canada, from Quebec City, actually, from my research team. where you get on two soils. We did exactly the same. We compared conventional and no-till for N2O emissions on two soil types, just nearby, about 200 meters away. So what we found is no effect on the sandy loam, on a very well-drained sandy loam, but double the emissions of the no-till compared to the conventional on the clay soil. And that's a very heavy clay soil, almost 60% clay in that situation. So what we conclude from this? Well, if data seem to indicate that in Brazil the no-till decreases emission, these data show that the no-till may also increase emissions and that there is an interaction with subtype. So those are, now let's look, I'm aware of 3 meta-analysis that looked in the literature to try to see what is the trend. I did it a little bit in a very crude way from Brazil. So if we look at the tree, well, 5 years ago, I did a very simple one where I looked at all the data that were published at the time. It was quite limited, but still, I came to the conclusion that the no-till would increase emissions compared to conventional in poorly drained soils, but decrease it in well-drained situations. So that was the conclusion at the time. Swan, in a master's thesis that I found on the internet and at Colorado State, supervised by Keith Bauschen and Steve Ogle, came to a similar conclusion last year. She looked at two factors controlling the difference between no-till and conventional. She looked at climate, humid or dry, and soil texture, low clay or high clay. So what she sees is that the emissions, like the no-till, yields greater emissions than conventional in clay soils, but not on low clay, high clay soils, but not on low clay soils, and that this effect is greater in the dry situation than in humid. But the most important conclusion when I looked at this data was that the soil type seemed to be more important than climate. So I think this seems that the effect of soil type seems to override the effect of climate in many situations. And there was no impact of the time since application. Like, it doesn't matter if the no-till had been adopted for 1 year, 5 years, or 10 years, or 20 years. This wasn't a factor in the conclusion. More recently this year, Chris Van Kessel at the University of California in Davis did another meta-analysis and came to those conclusions, 2 main conclusions, that no-till reduced emission compared to conventional 10 years after adoption, not before, and especially on the dry climates. And I think it's a very interesting thing, depending also how deep the fertilizer was placed. But if we try to see the general trend and all that, all 3 meta-analyses agree that there's an interaction with subtype. And all 3 meta-analyses suggest that the emissions due to no-till will be lower if the soil is well drained. So this is for no-till. Other conservation practices, nitrogen management in no-till. We'll look at how deep we place or where we place the fertilizer. Sorry. And the type, also the form of fertilizer of the N amendment that we bring to the soil. So here's the situation. So you can bring the fertilizer at the surface, but it's very prone to volatilization, especially if you have urea or manure. So another way to avoid those is to inject or subsurface band the fertilizer near the crop row. So when you do that, what is the impact on N2O? Well, first you improve the use efficiency, so you lower the concentration of N in the soil for microbes to use and to nitrify and use N2O. And you also decrease the volume of soil that is in contact with the N amendment. So this is a tendency to decrease the potential for emission.
On the other hand, you increase the concentration in the land. And you have also having a less aerated environment into the soil than at the surface. And also, because of, if it's urea, of course, because of the high pH in the band after urea hydrolysis, then you may have N2O nitrite accumulation, which we know is a precursor of N2O. All these tend to increase. So again, what is the net balance of those effects? Well, when you look at the literature, pretty much everybody agrees that banding results in greater values than surface broadcast in terms of N2O emissions. The work by Alberson and Congresso and Engel was in no-till situation. So that's what the data tells, that surpassing band or injecting is increasing the emission. A couple of other results that I found in the literature was there may be also a depth factor, just what Van Kessel found in his meta-analysis. Also, it's important also to include the indirect emission, because you apply fertilizer in the soil, you incorporate it, you don't have as much ammonia volatilization, then you don't have as much indirect emission of N2O, and those should be factored in. And since you may also improve the end-use efficiency, you may be able to decrease the N rate when you subsurface band or inject compared to surface. So all these tend to decrease the emissions. Here I have data from Celso and Ezekiel and Santa Maria University, and you see that injecting the slurry, big slurry, increased by a factor of 3 the N2O emissions. So pretty clearly, when you inject or subsurface band the N inputs, you will increase N2O emissions. However, it would be needed to also consider the indirect emissions to get a clear picture of the net results. Now, in conservation agriculture, I think it's fair to say that we want to value the manure nutrients. So they could be used in place of mineral fertilizer. So if you replace the mineral fertilizer with a manure, either at the surface or injected or subsurface banded, what is the impact on N2O? So again, you'll have factors that will tend to increase the emissions because you increase the available C for the electrification, creating hotspots because of the decomposition of that organic material. That will tend to increase the nitrification and N2O emission. And on the other side, of course, you have a big saving because you don't have all the fossil fuel required for production and transport of the mineral fertilizer. So when we look at the results of the literature, they indicate that manure may increase N2O emission, especially compared to synthetic N fertilizer, especially if they are applied on a soil with a low carbon content. But while on the soil with high carbon content, they are really no effect, or even lower. And a recent meta-analysis by one of my students indicates that in the global literature, when you compare synthetic and organic N for N2O production, there's a slightly lower values for organic than mineral. And also, again, we need to consider the saving of the CO2 cost, the fossil fuel cost for the production of the fertilizer. The other tool or practice that we can use in conservation agriculture to limit N2O are nitrification inhibitors. In theory, they are very, very efficient because if you inhibit or stop nitrification, there's no, of course, N2O emitted from nitrification, but also it results in very low amount of nitrate available for the nitrification. So the two of them, the two reaction rates being low, the N2O production should be low. And that's what we want, that's what we see in the literature, up to 90% reduction compared to untreated urea. Pig slurry is very efficient to, again, data from the Santa Maria University, where you see that injection, adding the CD to injected pig acids were reduced by a factor of 3. If you remember the previous slide, actually it brings the value even lower than what we did measure for surface application. So, very, very efficient. But I guess the question is it economically justified? And Harris, in a recent paper in Australia, thinks that it may not quite be economically justified yet. The other type of fertilizer that we can use to have in no-till to prevent the large accumulation or high concentration event in the soil are the slow-release fertilizers. In theory, it decreases the N2O production by decreasing the soil N concentration. And they've been proved to be pretty efficient in no-till situation. And again, there's a work by Zaletta here in Brazil, and the work by Versman Del Rosso under irrigated no-till corn in Colorado. Very efficient. A couple of reports of increases in special situations, but they seem to be very well adapted to the no-till situation. So that would be a valid option. Now, enough for the end fertilizer. Another conservation agriculture practice is to include legumes in the rotation. And it could be for the main crops, or it could be for the cover crops. It's a valid question, because if we go back in 1997, when IPCC first produced their guidelines for national inventories of soil N2O, legumes was a major source. In Canada at the time, they were responsible for almost 1/4 of all our agricultural emissions. But this is, I would add myself a little bit here. Anyway, but now it has changed those things, because we have demonstrated that biological fixation is not the source of N2O during the active growth of the crop. And of course, there will be an increased emissions when the enriched legume residues are plowed under after the harvest. But this increase due to the higher N level in the residues will not offset the gain that we have by not using N fertilizer during the growing season. So introducing legumes in the rotation will lead to a net increase in N2O emission from the conservation agriculture system. Now, another major factor in conservation agriculture are the cover crops. As I read, maintaining a vegetation cover is one of the key principles in conservation agriculture. So several crops can be used for that. And again, we have to distinguish between the period during which the cover crop is actively growing to the one that is after it's being killed to plant the following crop. During the active growth, there's plenty of factors that will decrease the potential for emission. They pump nitrate, they pump water, they lower soil temperature, they lower leaching, so decrease the indirect emission. While after the kill, though, there are factors that will increase emissions. There'll be a flush of fresh organic matter full of available carbon and mineral nitrogen. And because of the rapid decomposition of that material, there will be also a lower redox potential that may trigger the nitrification and increase N2O emissions. And what do we see when we look at the literature? This is a paper by Søren Pedersen in Denmark, and he compared conventional, reduced tillage and no-till, and in all situations, the presence of the cover crop in the whole seed year of farming increased the total emissions. And most of the difference occurred after the kill of the crop, not during the growth, but after the kill. The same observation by Gomez here in Brazil, and they added that the impact after kill on N2O emission was proportional to the N content of the crop material. Another work here by Giacomini, again in Santa Maria University, they did measure the N2O emission after the chemical kill of a series of different types of cover crops, and all of them led to greater values under control. Then we come to the question, is it a time bomb? Well, actually for N2O, I would call the cover crops a time bomb. You reduce, the emissions during the active growing period, but when you kill it, then it really frees up all the carbon and nitrogen substrate that do increase emissions. But is there a better way to kill the crop? Is it better to plow it under or chemical kill? I know in conventional agriculture you won't plow it under. So let's see what is best. Data from Canada show that if you have a poorly drained soil situation, chemical kill may actually increase emissions compared to plow. Because the plow, then the inversion plow, will bring the material deeper in the soil in very anaerobic conditions where the nitrification of the material of the nitrate may actually all the way to N2 and no N2O. While close to the surface, there's more oxygen and there's more N2O produced. The inverse has been observed here by low carbo in Brazil. Lower emissions on the chemical than on the plow, which is good news for conservation agriculture in Brazil. So, in conclusion, for the cover crops, the herbicide kill maybe is better adapted to the well-irrigated conditions. Now, if we do we've looked at every or several conservation practices, and now each of them individually impact on N2O. So now let's try to see how, when we put all of them together, if we can see what is the net balance for the conservation practices over the whole year. Values above the x-axis are increases in emission, and values below the x-axis are reduction. So here you have no-till. So no-till will both could increase or decrease depending if it's adopted on a well-irrigated soil and a poorly irrigated soil. Injection of nitrogen, either mineral or manure or organic, will increase emission. Use of innovative or advanced form of nitrogen fertilizer will decrease. Use of manure instead of mineral fertilizer will slightly decrease the emissions. Introduction of legume in irrigation will decrease the emission, but cover crop will increase the emission. So what can we do the net effect? Well, it could be both ways. It could be, let's say if we have the perfect storm. If you apply, if you adopt no-till on a poorly drained soil and you use cover crops, you will have an increase in emission compared to conventional. But if you have the best scenario, if you adopt no-till on the conventional, on the well-drained soil, and you adopt intelligent way, I would say, to fertilize, then you will offset the negative impact of cover crops, and you will still have a net benefit. So I ask myself, well, but in the real world, what it is? Well, in the real world, usually there are two practices that are almost inherent to conservation practices. It's the no-till and the cover crops. So it means that if you practice no-till on a well-irrigated soil, it's likely that part of it or all of the benefit may just be offset by the increase in emissions due to the cover crops. I'm not saying about if we use it on a poorly irrigated soil, it will be really starting negative. So we may ask if maybe the net balance between the conservation practices as being a net source, an increase or a decrease in N2O emission may actually reside in those N management, the management of the N inputs in the soil. So I throw that as a question for discussion anyway. So the key in conservation practices for N2O may not be no-till actually. So now we'll talk about that's it for N2O. Now we'll pass to ammonia. And ammonia, we'll see how we can manage slurries essentially and urea in order to decrease the volatilization. Volatilization, well, ammonia, we're not talking like N2O here. N2O you're going to lose between 1% and 4% of the N that you have. It's not much, and in an agronomic side, it won't make a big difference if you lose a lot or little as N2O. But not ammonia. With ammonia, you're talking about big numbers. In Brazil, I found that you're using tons of urea annually on agricultural soils. If we assume a pretty conservative loss factor of 10% and a price of 900 reales per metric ton of urea, and then we're close to $300 million worth of loss of urea due to ammonia volatilization in Brazil. And this is not including what is lost during the storage of animal manures and when after they are applied to the soil. Altogether, it makes very, very big numbers. So why do we care about ammonia? Well, it's very clear. Crop yields. If you lose 10, 20, 30% of the nitrogen that you apply, and it was intended to feed the crop, and you lose it to the atmosphere, there will be an impact likely on the crop. Money, you didn't buy urea to send it to the atmosphere. Environment, we know that after this nitrogen has been emitted, it falls down in other ecosystems where it reduces biodiversity, contributes to soil acidification, and other negative effects. And also human health, because it leads to respiratory diseases for some people. The reason is that when ammonia is emitted in the atmosphere, it's one of the rare bases in the atmosphere, and it reacts very quickly with acids. Nitric acid, sulfuric acid produced by cars, produced by mills and factories, industrial activities, and it produces salts, nitrates, sulfates, that are very, very fine particles in the atmosphere, less than 2.5 microns. And those created are contributing to smog. Like in Los Angeles, essentially, recent measurements published last year showed that the smog that you see in Los Angeles actually comes from the cars and the cows, because it's the ammonia emitted from the cow manure around Los Angeles that is reacting with the acids produced by exhaust of cars that do produce those particles that create the smogs and make some people sick. So in Canada and Europe, I don't know about Brazil, but it is on the list of toxic contaminants in the atmosphere that we have to decrease the concentration. What are the conditions for ammonia volatilization to occur? Well, you need two things. Of course, you need ammonia. And what do you need to get ammonia? You need ammonium. Ammonium comes from essentially two sources here, slurries and urea. And once you have ammonium, it's got to be solubilized, because if it's dry, you only have the NH4 plus 4. If you add it in water, if you dissolve it in water, then you have the two ionic forms, NH3 and NH4 plus. And also you need water for the hydrolysis of urea. So you need water to have ammonia. And of course pH, you need a pH greater than 7. Below 7, there's only the NH4 form that is present, so there's no potential for volatilization if the pH is below 7. And temperature, because once it's in solution, the amount of dissolved gas that will actually be released in the atmosphere is a function of temperature, as described by Henry's law. So that's for the presence of ammonia. The second condition is going to be exposed to the atmosphere. If there's a physical barrier, they will between the ammonia and the atmosphere, the emission, the volatilization will be decreased as a function of the resistance to diffusion. When we place rich, NH4-rich material at the soil surface, we get big ammonia emission. Urea, those are maximum values. You can get up to 60% of the urea that can be lost. Pig slurry, you usually get about 50 to 70% of the total air that is ammonium air. So you can lose up to 30-40% of total air. Not all materials are equal. Among the organic, clearly slurries, because of what I just told you about the high content in ammonium, and in the mineral forms, urea, for several reasons we can discuss another time. But those are the two forms that are the main sources of ammonia volatilization. So if we incorporate rapidly those residues, you will decrease the emission tremendously by 80%, 90% compared to surface. So you say, why not? Well, In a situation of no-till, you cannot conventionally incorporate those materials for the reason that you don't want to disturb the surface, you want to keep your residue covered. So it's incompatible, so that will tend to increase. And also you've got at the surface crop residues, sometimes large amount of crop residues, that have two effects. One, it retards the infiltration of the material, so it increases the exposure to the atmosphere. And also, plant material and the fungi that decompose that material are very rich in urease. So if you apply urea on crop residues, it will be hydrolyzed to ammonia and ammonia much faster and increase the emissions as well. So I would call that applying N-rich materials at the surface, NH4-rich material at the surface of a no-till is the perfect storm. So what can we do to reduce these ammonia emissions? Well, you have injection, create a barrier between the ammonia and the atmosphere. And you have crop residues. I've just mentioned how bad they can be, but could we work with them instead of just having the bad effects? And also how irrigation could influence. And with the help of God, how could rain also influence the volatilization? And finally, we'll look at the urease inhibitors as a tool to limit the emissions. So, a rapid incorporation in the soil decreases emissions. They are 80%, very clear. But again, we can't do that in no-till. So, if we inject, you only disturb a small fraction of the surface, so you leave the residues on the surface, but you place your nitrogen below the surface. You don't create a barrier between the end source and the atmosphere. So what do you see? Well, we see a reduction here with slurry and urea, about a half reduction, 50% reduction. But that's much less than what we've just seen, like 80, 90% if you do a conventional incorporation. Why is it so? Well, in that experiment, we realized that it's pretty hard for slurry to actually incorporate in bands large volume of slurry. We're limited by the volume of the slot, and very often it will sprout at the surface, and we will not be able to actually inject all the manure efficiently. Oh, it's okay, that explains the reduction. But not for urea. Urea, we really band it at 5 centimeter depth, very much isolated from the surface. So why is it so? So the reason is that when you inject urea in band, and the urea is being hydrolyzed, there's a big increase in soil pH. Here, 1.5 unit, and a non-unit, 1 unit of pH is 10 times greater concentration or lower concentration of protons in the soil. So what happens is that for the hydrolysis of each mole of urea, it requires 2 moles of protons. So a big uptake of proton by the process, and in a very restricted volume. So then the response of pH in that area is very high. And as you recall, the higher the pH, the more we find the ammonium in the NH3 form. So the more the pH increase, for the same concentration in ammonium, you have much more ammonia. So a very intense source of ammonia, 5 centimeters deep in the soil, also result in 50% less losses, only 50% less losses. So we looked, we kept looking for ways and learning more about how we could deal with this, these emissions when we inject urea. So we looked at how would the rate of application impact on the total emissions. And we see here that with the increase in application rate of urea, we see a non-linear increase of the percentage of applied N. So a non-linear response of the volatilization to an increase in N rate. What I'm not showing here is that this is only the case on acidic soil. If you do that on alkaline soil, because of their pH buffer capacity, most of the carbonates, the calcium carbonates, they will limit the increase in pH, and the increase will be linear. So different a little bit than acidic soils. So that's the impact of pH. So, and now what does the impact of the depth of placement? You know, the previous experiment I showed you was the urea was placed at 5 centimeters. So what if we place it shallower? What if we place it deeper? So here we banded urea at the surface, this is the 0 depth, and at 2.5, 5, 7.5, and 10. And you see how it decreases. Pretty much linearly in the first 7.5 centimeters, because it reached pretty much 0 there, and no further decrease, of course, when you get to 10. So from this experiment, it was concluded that urea should not be placed shallower than 5 centimeters to limit ammonia emissions from situation where it is injected in the soil. Now we went further just our own study. We looked in the literature, all the studies in which they made direct comparison between surface application of urea and placement at different depth in the soil. And when we express the results in a fraction of what was observed when the urea was applied at the soil surface, we see a very good relationship. And what we get there is that we get a linear decrease with depth of about 12% of what the values were at the surface per centimeter of incorporation. So that could be used as a rough estimate if you plan to incorporate urea to decrease ammonia volatilization. So this is for the injection. Now if we go to the crop residues. In one experiment, we applied urea to a freshly tilled soil, and we applied urea to the no-till soil. And we did this at three different sites. And what we saw, much greater ammonia emissions on the no-till than on the till soils. And the reason, when we look at the right-hand side, is that the urea's activity was so much higher at the surface of the no-till soil compared to that of the freshly tilled soil. And that's because, again, the plant residues are very rich. Plants in their tissues translocate the N in the form of urea, so they need to have urease to make it available at different other locations in the plant. And fungi also in their tissues are fairly high urease content. So that's the reason why. So is there a way we could use residues working with us again, instead of against us? So we did this other experiment, and actually that has been suggested by a farmer, a no-till farmer near Montreal in Canada. He said, well, what if I do this? He said, what if I broadcast the urea on the crop residue, and then I pass with a very slight shaker, that just moves the residue, that does not till the soil, but shakes the residue so that the urea granules will actually fall through the residues to the soil surface. So, well, we'll try that. So that's what we tried. And what we measured is that, I call that under residues in bare soil, but we had a 50% decrease just by making sure that the urea granules were not sitting on the crop residues, but fell between the cracks, if you mean, between the residues on the soil surface. So it seems that the crop residues, in some sort, could be actually our friends in this. Okay, rainfall, irrigation. In the study that we have not published yet, we said that irrigation could reduce, following surface broadcast of urea, that was by 75%. And 12 millimeters of rain were enough. Sans Cadena, I believe they are Spanish, in the same situation, they also demonstrated that 7 and 14 millimeters of irrigation or rainfall decreases significantly, almost 80–90% the ammonia volatilization. But interestingly, the very light irrigation, 3 millimeters, actually increased emission. And you see the non-linear impact of soil water on ammonia volatilization. First, to have volatilization, you need to have the ammonia man that is dissolve in water. So if you start with a very dry situation, the first impact of water will actually be to dissolve ammonium, create ammonia, and increase volatilization. So it's why that if you just have a little sprinkle, a very light rain, it will likely increase volatilization. But if the rain is strong enough to actually infiltrate the soil and brings with it the ammonium deeper into the soil, it acts like it as an incorporation. Similar thing here by Alcon et al. In 2001 in the American Soils Journal, where they said that about 7 millimeters decreased by 80% the volatilization. Here I'm bringing your attention to the last sentence in this box here, is that it's important that the rainfall occurs pretty shortly after urea application to the soil surface. Why? Is it because the urea molecule is neutral, it's not charged. So when it's dissolved in water, it will infiltrate very easily, and with the water actually, it's going to follow the water through very efficiently and will incorporate the material below the soil surface. But if you wait, let's say, more than 3 days, you will have a significant fraction of the urea N that has been hydrolyzed to ammonia. And ammonia is a charged molecule that will be fixed or attracted at soil, on soil particles, so that the infiltration will be much less efficient. So if you plan to infiltrate urea with irrigation, it's better if it has to be in the couple of days that follows the application. Now the urease inhibitors. Again, I went and I surveyed the literature, and I found 13 studies in the field comparing surface broadcast of urea and with and without NDPT, the most common urease inhibitor. 3 of those studies actually were done here in Brazil. So what did we find? What did I find? I find that very significant decrease in emissions, between 40 and 90%. And this is even without any rainfall. Because the nice thing about the urease inhibitor is it's going to keep the urea longer on the urea form. So you've got a longer window to apply irrigation or to wait for a rainfall. So, and these studies will not include this effect. So even without that, very, very significant decreases in emissions. Same thing for the studies under lab conditions, where the efficiency and reduction vary between 30 and 90%. When I did out the average of all this, well, it's good. Like the lab and the field studies agreed, and they were approximately 60% reduction, with fairly small standard deviation. So fairly reliable efficiency of urease inhibitor application on ammonia. And if you look at if you refer to the graph I just presented about the impact of incorporation depth, that 60% corresponds approximately to a 4 centimeter depth incorporation. So using urease inhibitor is just about like incorporating to 4 centimeter in terms of reduction in emission. So here I did the same on this little graph for the ammonia volatilization as I did before for the N2O. So when you apply slurries, amino slurries or urea to the soil surface, it is the perfect storm. You can lose up to 60% of the N that you have applied to the soil surface. Likely less, but possibly up to that. If you apply under the residue, you are probably going to reduce by half those emissions. Injection, even a little bit more. Urease inhibitors, about 60%. And irrigation, the same order as injection. So that shows that the tools that you have, the practices that you have in conservation agriculture to limit this big problem that is the ammonia emission when you deal with ammonium-rich materials in the field. So in conclusions here I have 2 slides, and I'm never too good at that, so what we should do in order to fix your research and everything, but I try to come up with a few things. In no-till for N2O, one thing that I think we should investigate more is actually the interaction between the form and the depth of N placement in no-till. Because when you have no-till, I mean, the first impact is that you stratify the organic material that you return as crop residue. So you very likely modify the microbial population with depth in the soil. So if you apply, for example, nitrate or ammonium in different places, it may likely have a different impact, both the form and the placement depth. So Rodney Venturea in Minneapolis at USDA has worked on this, and I hope you do some more work because I think it's one of the key things. The factors that control the activity of N2O reductase, as we briefly mentioned at the beginning, when you have denitrification, you have two gaseous end products, N2O or N2. So what is the ratio of both? It's critical in terms of N2O emissions. It's also critical in terms of getting rid of that reactive nitrogen that accumulates in the biosphere of the planet. So I think we need more more research to better understand. People in Norway have worked and saw that when you are in pretty acidic conditions, it does affect the impact of the N2O reductase. So lighting those cells likely will decrease the N2O emission. So those kind of avenues. And we do need badly LCAs. I mean, especially when the topic of my talk today, conservation practices. There's not one, there's 2, 3, 4, 5 different options that can be made, and it's over the whole year. So you've got to consider not only what one decision or one practice makes, but how, when it is put together with the other ones, what is the net effect? And that we don't have too many. For the N2O, for the ammonia, we know ammonia much better than N2O. Ammonia is a very simple one. Ammonia volatilization is a function of physical, chemical equilibrium. Pretty easy to predict, as opposed to N2O. N2O, the humbling gas, the one that makes you feel bad all the time. The ammonia here, what I thought we should try to develop are some practical things, like commercial applicators to apply that enriched material in an innovative way. As mentioned, this thing that we can apply the agric granules below the crop residues just by shaping the residues is one example. Injection, I don't think we can do this very well still. And also, this thing of when urea is injected, subsurface depth, there's all kind of things that we need to consider. What is the initial pH of the soil? That will have a major impact. The pH buffer capacity. The water content, and because we're talking about diffusion of the material, and ammonia is very hydrophile, it will dissolve in water very, very easily. And soil porosity on top of the band. When you do that with the machine, how well the machine packs back the soil on top of the urea. Those are things I think we know to give better advice and more quantitative advice to farmers that want to adopt those practices. Muy obrigado.